Question 1. The audit findings indicate significant water staining on the ceiling of a residential unit's bathroom. The staining is located directly below a section of the master bathroom. The auditor has noted this as a potential plumbing issue requiring immediate attention. As the certified plumbing designer responsible for the building's plumbing systems, what is the most appropriate initial diagnostic approach? Option A. Conduct a thorough visual inspection of all plumbing fixtures, supply lines, and drainage components within the master bathroom and directly above the stained area, including checking for visible signs of corrosion, damage, or loose connections. Option B. Advise the building management to simply repaint the stained ceiling to address the aesthetic issue. Option C. Immediately recommend the replacement of the toilet in the master bathroom, as toilets are a common source of leaks that can manifest as ceiling stains. Option D. Suggest a general inspection of the building's main water supply line for any pressure fluctuations that might be causing intermittent leaks. Correct answer is A. Conduct a thorough visual inspection of all plumbing fixtures, supply lines, and drainage components within the master bathroom and directly above the stained area, including checking for visible signs of corrosion, damage, or loose connections. Explanation. This scenario presents a professional challenge because it requires the certified plumbing designer to move beyond simple identification of a problem to a diagnostic process that considers multiple potential causes and their implications within the context of established codes and standards. The auditor's observation is a symptom, not a root cause, and a hasty conclusion could lead to ineffective repairs, code violations, or further damage. Careful judgment is required to systematically investigate, ensuring that the proposed solution is not only effective but also compliant and safe. The correct approach involves a systematic investigation that begins with gathering more information about the specific symptoms and the surrounding environment. This includes understanding the nature of the water staining, its location relative to known plumbing fixtures and drainage lines, and any recent changes or events that might be relevant. This methodical approach aligns with the principles of good engineering practice and the implicit requirement within plumbing codes to design and maintain systems that are safe, functional, and durable. Specifically, codes like the International Plumbing Code, IPC, or Uniform Plumbing Code, UPC, depending on the adopted jurisdiction for the exam, mandate that plumbing systems be installed in a manner that prevents leaks and allows for proper drainage. Diagnosing a leak requires understanding the system's design and operation to pinpoint the source, which could be a fixture, a pipe, a joint, or an appliance. An incorrect approach of immediately assuming a specific fixture is the sole cause fails to consider other possibilities and bypasses the necessary diagnostic steps. This could lead to unnecessary replacement of functional fixture while the actual leak source, perhaps a hidden pipe or joint, remains unaddressed, potentially causing further damage and violating the code's intent to ensure a leak-free system. Another incorrect approach of focusing solely on the visible stain without investigating the underlying cause is also professionally unacceptable. The stain is a secondary effect. Ignoring the primary cause means the problem will likely recur, leading to continued system degradation and potential health hazards, e.g., mold growth, which contravenes the code's requirement for a safe and sanitary plumbing system. A third incorrect approach of recommending a general pipe repair without specific identification of the damaged section or the nature of the damage is equally flawed. This lacks the precision required for effective repair, could lead to unnecessary work, and may not address the actual failure mode, potentially violating code requirements for proper repair and material usage. The professional decision-making process for similar situations should involve a structured diagnostic methodology. 1. Observe and document the symptoms thoroughly. 2. Gather contextual information, history, surrounding conditions, system layout. 3. Formulate hypotheses about potential causes. 4. Test hypotheses through inspection, observation, and potentially non-destructive methods. 5. Identify the root cause. 6. Propose solutions that are code-compliant, effective, and address the root cause. 7. Document the findings and propose solution. Question 2. Process analysis reveals a multi-story residential building where the municipal water supply pressure frequently exceeds 80 psi, and the building's plumbing system is designed to serve fixtures on upper floors. The design also includes a water heater. The designer is considering installing a pressure-reducing valve, PRV, to manage the high incoming pressure. What is the most critical consideration regarding the integration of a PRV in this scenario to ensure both system integrity and regulatory compliance? Option A. Verifying that the PRV is set to a pressure that is slightly lower than the maximum allowable pressure for the building's piping. Option B. Installing a single check valve immediately downstream of the PRV to prevent any backflow from the building system into the municipal supply. Option C. Ensuring that an approved thermal expansion control device is installed on the cold water supply to the water heater to manage pressure increases due to thermal expansion. Option D. Selecting a PRV with a maximum flow rate that can accommodate the peak demand of the entire building. The correct answer is C. Ensuring that an approved thermal expansion control device is installed on the cold water supply to the water heater to manage pressure increases due to thermal expansion. Explanation: this scenario is professionally challenging because it requires the plumbing designer to balance competing demands of water system performance, safety, and regulatory compliance. The core challenge lies in ensuring adequate water pressure for intended use, while simultaneously protecting the potable water supply from contamination and managing the effects of thermal expansion, all within the strict confines of the certified plumbing designer exam's specified regulatory framework. Careful judgment is required to select the most appropriate and compliant combination of devices. The correct approach involves a comprehensive understanding of the interplay between pressure-reducing valves, PRV, backflow prevention devices, and thermal expansion control mechanisms as mandated by the relevant plumbing codes and standards. Specifically, it requires recognizing that a PRV, while reducing incoming municipal pressure, can create a condition where thermal expansion within the building's hot water system needs to be managed. This necessitates the installation of an approved thermal expansion control device, such as an expansion tank or an automatic pressure relief valve, located on the cold water supply side of the water heater. Furthermore, the selection and placement of backflow prevention devices, like an RPZ or double check valve, must be based on the specific cross-connection hazard identified, ensuring compliance with backflow prevention requirements to safeguard the public water supply. This integrated approach ensures both system functionality and public health protection. An incorrect approach would be to install a PRV without addressing thermal expansion. This failure violates the principle of preventing overpressurization within the building's plumbing system, which can lead to fixture damage, pipe bursts, and potential safety hazards. It directly contravenes code requirements that mandate thermal expansion control when a backflow prevention device or a pressure-reducing valve creates a closed system. Another incorrect approach would be to install a backflow prevention device without considering the impact of reduced incoming pressure on the building's water supply needs. While backflow prevention is critical, failing to ensure adequate service pressure can lead to user complaints and system underperformance, potentially necessitating a PRV. However, if a PRV is installed, the thermal expansion issue must be addressed. A third incorrect approach would be to install a PRV and a thermal expansion control device, but select an inappropriate type of backflow prevention device for the identified hazard. For instance, using a simple check valve where an RPZ is required by code would represent a significant regulatory failure and a risk to public health. The selection of backflow prevention must be directly tied to the assessed risk of contamination. Professional reasoning in such situations involves a systematic process. First, understanding the building's intended water use and pressure requirements. Second, identifying potential cross-connection hazards and determining the appropriate level of backflow prevention required by code. Third, assessing the incoming municipal water pressure and determining if a PRV is necessary. Fourth, if a PRV or backflow prevention device creates a closed system, ensuring that thermal expansion is adequately controlled according to code. Finally, selecting specific devices that are listed and approved for their intended use and comply with all applicable standards and regulations. Question 3. Risk assessment procedures indicate that a new multi-unit residential building will have a potable water distribution system with moderate water hardness and a slightly acidic pH. The design team is considering several pipe materials for the domestic hot and cold water lines. Which of the following approaches best ensures compliance with public health standards and long-term system integrity for this specific application? Option A. Choose the least expensive pipe material available that can handle the projected water pressure, assuming that all commonly available plumbing pipes are suitable for potable water. Option B. Prioritize a pipe material that offers the fastest installation time, as this will reduce overall construction costs and project duration, without specific regard for its long-term performance in the local water chemistry. Option C. Select a pipe material that is explicitly listed and certified for potable water use by a recognized third-party testing agency, and is known to be resistant to corrosion in moderately hard, slightly acidic water conditions, as per the requirements of the governing plumbing code. Option D. Opt for a pipe material that has been successfully used in similar climate zones for non-potable water applications, as this suggests general durability. The correct answer is C. Select a pipe material that is explicitly listed and certified for potable water use by a recognized third-party testing agency, and is known to be resistant to corrosion in moderately hard, slightly acidic water conditions, as per the requirements of the governing plumbing code. Explanation: this scenario presents a professional challenge because the selection of pipe material for a potable water distribution system directly impacts public health, system longevity, and operational efficiency. A failure to select appropriate materials can lead to premature system failure, contamination of drinking water, and significant financial repercussions for the building owner and potentially the public. The certified plumbing designer must exercise careful judgment, balancing performance requirements, regulatory compliance, and cost-effectiveness. The correct approach involves selecting a pipe material that is certified for potable water use, resistant to corrosion and degradation in the specific water chemistry of the jurisdiction, and suitable for the intended pressure and temperature conditions, all while adhering to the prescriptive requirements of the governing plumbing code. This approach is right because it prioritizes public health and safety by ensuring the integrity of the water supply. Specifically, it aligns with the fundamental principles of plumbing design that mandate the use of materials approved for potable water to prevent leaching of harmful substances and to maintain water quality. Ethical considerations also demand that the designer choose materials that will perform reliably over the expected lifespan of the system, thereby avoiding future health risks and costly repairs. An incorrect approach that relies solely on cost-effectiveness without verifying potable water certification is professionally unacceptable. This failure constitutes a regulatory violation because it bypasses the explicit requirements of plumbing codes that mandate approved materials for potable water systems. Ethically, it demonstrates a disregard for public health by potentially introducing hazardous materials into the water supply. Another incorrect approach that selects a material based on historical use in non-potable applications, without confirming its suitability and certification for potable water, is also professionally unacceptable. This is a regulatory failure, as it ignores the distinct requirements for potable water systems, which often differ significantly from those for other water uses. It also presents an ethical risk by potentially exposing users to contaminants not permitted in drinking water. A third incorrect approach that prioritizes ease of installation over material compatibility with the local water chemistry is professionally unacceptable. This is a regulatory failure because plumbing codes often specify material requirements that are linked to water quality to prevent premature failure due to corrosion or other degradation, which can compromise the system's safety and functionality. Ethically, it risks system failure and potential health hazards due to material incompatibility. The professional decision-making process for similar situations should involve a systematic review of project requirements, including water quality analysis, pressure and temperature demands, and intended use of the water. This should be followed by a thorough examination of available pipe materials, cross-referencing their properties against the project needs, and crucially, against the prescriptive requirements and material approval lists within the applicable plumbing code. A risk-based assessment should then be performed to evaluate the long-term performance and safety implications of each viable material option, ensuring compliance with both regulatory mandates and ethical obligations to protect public health. Question 4. Quality control measures reveal that the installed building sewer line has a slightly reduced slope in one section compared to the approved design plans, and a septic tank has been placed closer to a well than the minimum setback distance specified in the local health department regulations. As the certified plumbing designer responsible for this project, what is the most appropriate immediate course of action? Option A. Immediately halt all further construction related to the sewer and septic system until the discrepancies are fully investigated and rectified according to the approved plans and applicable regulations. Option B. Trust the contractor's verbal assurance that they will make the necessary adjustments during the backfilling process to meet code requirements. Option C. Proceed with the next phase of the project, assuming the quality control team will monitor these specific issues closely and report any significant problems. Option D. Advise the contractor that these issues appear minor and can likely be addressed during final system testing without impacting the project timeline. The correct answer is A. Immediately halt all further construction related to the sewer and septic system until the discrepancies are fully investigated and rectified according to the approved plans and applicable regulations. Explanation. Scenario analysis. This scenario presents a professional challenge due to the potential for significant environmental contamination and public health risks if a building's sewer and septic system are not designed and installed in strict accordance with applicable regulations. The challenge lies in identifying and rectifying deviations from approved plans and specifications that could compromise the system's integrity and functionality. A certified plumbing designer must exercise meticulous judgment to ensure compliance and prevent future failures. Correct approach analysis. The correct approach involves a thorough review of the quality control reports, cross-referencing them with the approved design plans and relevant local and state plumbing codes, and then initiating a site inspection to verify the reported discrepancies. This approach is correct because it directly addresses the identified issues by confirming their existence and extent in the field, which is a fundamental requirement of ensuring construction aligns with the approved design and regulatory standards. Specifically, this aligns with the responsibilities of a plumbing designer to oversee the implementation of their designs and ensure compliance with codes such as the International Plumbing Code, IPC, or state-specific amendments, which mandate proper installation of building sewers and septic systems to prevent leaks, backups, and environmental pollution. Ethical obligations also demand that the designer act to protect public health and safety. Incorrect approaches analysis. Dismissing the quality control reports without independent verification is an incorrect approach because it abdicates the designer's responsibility to ensure compliance and could lead to the installation of a faulty system. This failure to investigate directly contravenes the principles of professional due diligence and code adherence, potentially violating regulations that require oversight of construction. Assuming the discrepancies are minor and will not impact system performance is also an incorrect approach. Even seemingly small deviations in pipe slope, joint integrity, or tank placement can lead to significant long-term problems, including system failure, groundwater contamination, and health hazards. This assumption demonstrates a lack of understanding of the critical tolerances required for sanitary sewer systems and septic installations, and a disregard for the precautionary principle inherent in public health regulations. Relying solely on the contractor's assurance that the issues will be corrected without direct verification is an incorrect approach. While professional relationships are important, the designer's ultimate responsibility is to the integrity of the design and its compliance with codes. The contractor's assurance, while potentially well-intentioned, does not substitute for the designer's professional obligation to confirm that corrections have been made correctly and in accordance with the approved plans and regulations. This failure to verify can lead to a breach of professional duty and potential liability. Professional reasoning. Professionals faced with such situations should follow a systematic process. 1. Acknowledge and document all reported issues. 2. Immediately cross-reference reported issues with approved design documents and relevant codes. 3. Initiate a site visit to independently assess the reported discrepancies. 4. Clearly communicate findings and required corrective actions to the contractor and relevant authorities. 5. Verify that all corrective actions have been implemented to the designer's satisfaction and in full compliance with regulations. 6. Maintain thorough documentation of all communications, inspections, and approvals. Question 5. Risk assessment procedures indicate that a proposed cost-saving measure for a new plumbing installation involves using a material that is significantly cheaper but may not meet the full performance and durability standards outlined in the relevant plumbing codes. The client is eager to implement this measure to reduce project costs. As the certified plumbing designer, what is the most appropriate course of action? Option A. Proceed with the installation of the cheaper material, assuming it will function adequately for the short term, and address any potential issues if they arise later. Option B. Prioritize the client's immediate financial savings and approve the use of the cheaper material, deferring full code compliance verification until after installation. Option C. Advise the client that the proposed material cannot be used as it does not meet the required plumbing code standards, and explain the potential risks and regulatory noncompliance. Option D. Recommend finding ways to circumvent the specific code requirements related to material performance to accommodate the client's cost-saving request. The correct answer is C. Advise the client that the proposed material cannot be used as it does not meet the required plumbing code standards, and explain the potential risks and regulatory noncompliance. Explanation. Scenario analysis. This scenario is professionally challenging because it requires the plumbing designer to balance competing stakeholder interests, the client's desire for cost savings versus the regulatory mandate for public health and safety. The designer must exercise sound professional judgment to ensure that cost-saving measures do not compromise the integrity or safety of the plumbing system, which could lead to significant health risks and legal liabilities. Correct approach analysis. The correct approach involves prioritizing compliance with all applicable plumbing codes and standards, even if it means advising the client against certain cost-saving measures that would violate these regulations. This is justified by the designer's ethical obligation to protect public health and safety, as mandated by professional engineering codes of ethics and the underlying principles of plumbing codes. The designer must clearly communicate the regulatory requirements and the potential consequences of non-compliance to the client. Incorrect approaches analysis. Advising the client to proceed with the proposed cost-saving measure without verifying its compliance with plumbing codes is an ethical and regulatory failure. This approach prioritizes client satisfaction over public safety and violates the designer's duty to uphold professional standards. It could lead to system failures, health hazards, and legal repercussions for the designer and the client. Suggesting the designer look the other way or find loopholes in the code to accommodate the cost-saving measure is a severe ethical breach. This demonstrates a disregard for the purpose of plumbing regulations, which is to prevent the spread of disease and ensure safe water supply and sanitation. Such an approach undermines the integrity of the profession and the regulatory system. Focusing solely on the client's immediate financial benefit without considering the long-term implications of code compliance is professionally irresponsible. While client satisfaction is important, it cannot supersede the legal and ethical requirements to design safe and functional systems. This approach neglects the designer's responsibility to ensure the system's longevity and public health impact. Professional reasoning. In situations involving potential conflicts between client desires and regulatory requirements, a plumbing designer should follow a structured decision-making process. First, thoroughly understand the client's request and the proposed cost-saving measure. Second, meticulously review all relevant plumbing codes, standards, and local ordinances to determine compliance. Third, if the proposed measure is non-compliant, clearly and professionally communicate the specific code violations and the associated risks to the client. Fourth, propose alternative compliance solutions that might achieve similar cost savings or explain why the proposed savings cannot be realized without compromising safety. Finally, document all communications and decisions thoroughly. Question 6. The evaluation methodology shows that a plumbing designer is tasked with selecting fixture types for a new public library. Considering the diverse user base, including children, adults, and individuals with disabilities, which approach best ensures a compliant, functional, and accessible design according to U.S. plumbing regulations and ADA guidelines? Option A. Choose fixtures based on their modern aesthetic appeal and brand recognition, assuming they will meet basic functional needs. Option B. Focus on high-capacity fixtures to accommodate peak usage without specific consideration for water conservation or ADA compliance. Option C. Prioritize fixtures that meet the minimum water supply and drainage requirements outlined in the International Plumbing Code, IPC, and ensure all selected fixtures comply with ADA accessibility standards for clear floor space and mounting heights. Option D. Select the most cost-effective fixtures available from manufacturers, focusing on ease of installation to minimize construction labor costs. The correct answer is C. Prioritize fixtures that meet the minimum water supply and drainage requirements outlined in the International Plumbing Code, IPC, and ensure all selected fixtures comply with ADA accessibility standards for clear floor space and mounting heights. Explanation. Scenario analysis. This scenario presents a professional challenge for a plumbing designer by requiring them to balance the functional needs of diverse building occupants with strict adherence to plumbing codes and standards. The challenge lies in selecting appropriate fixture types that not only meet the basic requirements of use, but also comply with accessibility mandates, water conservation goals, and public health considerations, all within the context of a specific jurisdiction's regulations. A failure to correctly interpret and apply these requirements can lead to non-compliant designs, costly rework, and potential health and safety risks. Correct approach analysis. The correct approach involves a thorough understanding of the Certified Plumbing Designer exam's jurisdiction, which is assumed to be the United States, referencing the International Plumbing Code, IPC, and relevant ADA, Americans with Disabilities Act guidelines. This approach prioritizes selecting fixture types that meet the minimum requirements for each category: water closets, urinals, lavatories, bathtubs, showers, and kitchen sinks, as defined by the IPC, ensuring proper trap seals, venting, and water supply. Crucially, it also integrates ADA requirements for accessibility, such as clear floor space, mounting heights, and reach ranges for lavatories, water closets, and bathtubs/showers. Water conservation is addressed by specifying low-flow fixtures where permitted by code and by considering the overall water demand calculation. This comprehensive approach ensures a design that is safe, functional, accessible, and compliant with all applicable regulations. Incorrect approach is analysis, an approach that solely focuses on the lowest initial cost of fixtures, without considering water efficiency, durability, or accessibility, is professionally unacceptable. This failure stems from a disregard for the long-term operational costs, environmental impact, and legal mandates for accessibility, which are integral to responsible plumbing design and are often codified. Another incorrect approach would be to select fixtures based on aesthetic preferences alone, ignoring their functional performance, water usage, and compliance with trap seal depth and venting requirements stipulated by the IPC. This prioritizes form over function and safety, leading to potential plumbing system failures and health hazards. Finally, an approach that overlooks ADA accessibility requirements for specific fixture types, such as lavatories and water closets, is a significant ethical and regulatory failure. This results in a design that is not usable by individuals with disabilities, violating federal law and ethical design principles. Professional reasoning. Professionals should adopt a systematic approach that begins with a thorough review of the project scope and the specific jurisdiction's adopted plumbing codes and standards. This includes understanding the intended occupancy of the building and the specific needs of its users. The next step is to identify and select fixture types that meet the minimum performance and safety requirements outlined in the code for each category. Simultaneously, accessibility standards such as the ADA must be integrated into the selection process for relevant fixtures. Water conservation goals should also be considered, opting for water-efficient fixtures where appropriate and permitted. Finally, a comprehensive review of the design against all applicable codes and standards should be conducted before finalizing the plans. Question 7. The assessment process reveals that a new residential development requires a primary water source. The certified plumbing designer is evaluating 3 potential options: connection to the existing municipal water supply, drilling a private well, and implementing a rainwater harvesting system for potable use. Considering the regulatory framework and best practices for ensuring public health and water quality, which approach represents the most prudent and compliant recommendation for a primary water source in a new development? Option A. Recommend connecting to the municipal water supply, provided it meets the development's demand and current water quality standards as verified by the local water authority. Option B. Recommend drilling a private well, assuming adequate groundwater is available, and conducting basic water quality tests for common contaminants. Option C. Recommend a combination of a private well and a rainwater harvesting system, prioritizing the well as the primary source due to perceived reliability. Option D. Recommend a comprehensive rainwater harvesting system as the sole primary source, focusing on collection and storage capacity for consistent supply. Correct answer is A. Recommend connecting to the municipal water supply, provided it meets the development's demand and current water quality standards as verified by the local water authority. Explanation. The assessment process reveals a common challenge in plumbing design, balancing the selection of a water source with the inherent risks and regulatory compliance. A certified plumbing designer must evaluate not only the availability and cost of a water source, but also its long-term reliability, quality, and the specific legal and health requirements governing its use. This scenario is professionally challenging because the designer is tasked with recommending a primary water source for a new development, requiring a comprehensive understanding of various water sources and their implications beyond simple supply. The decision impacts public health, environmental sustainability, and the economic viability of the project. The correct approach involves a thorough evaluation of municipal water, wells, and rainwater harvesting, considering their respective characteristics against the project's needs and the governing regulatory framework. This includes assessing the reliability and quality of municipal water, the geological and hydrogeological suitability and potential contamination risks of wells, and the collection, storage, treatment, and regulatory compliance aspects of rainwater harvesting. The designer must prioritize a source that meets all applicable health and safety standards, ensures a consistent supply, and is sustainable. For new development, a reliable and regulated municipal supply is often the most straightforward and compliant option, provided it meets demand and quality standards. This aligns with the principle of prioritizing public health and safety by utilizing a source subject to stringent public health oversight and treatment protocols. An incorrect approach would be to solely focus on the initial cost or perceived simplicity of a particular source without a full regulatory and risk assessment. Instance, recommending a private well without conducting thorough water quality testing and ensuring compliance with local well construction and water quality regulations is a significant failure. This overlooks potential contamination from groundwater sources, which can pose serious health risks and lead to costly remediation. Similarly, proposing rainwater harvesting as the sole primary source without adequately addressing storage capacity, treatment for potable use, and compliance with local ordinances regarding its use for drinking water would be a regulatory failure. Many jurisdictions have specific requirements for rainwater harvesting systems, especially if the water is intended for potable purposes, and failing to meet these can result in non-compliance and health hazards. Relying on a municipal supply without verifying its capacity to meet the development's demand and its adherence to current water quality standards is also an oversight, potentially leading to supply issues and health concerns. Professional decision-making in such situations requires a systematic process. First, understand the project's specific needs and constraints. Second, research and understand the characteristics, advantages, and disadvantages of each potential water source. Third, critically evaluate each source against the applicable regulatory framework, including local, state, and federal health and environmental codes. Fourth, conduct a risk assessment for each source, considering reliability, quality, and potential for contamination. Finally, select the source that best balances project requirements, regulatory compliance, public health, and long-term sustainability, documenting the rationale for the decision. Question 8. The performance metrics show that a proposed commercial building's sanitary drainage system is designed to handle a significant load. The designer is considering using Schedule 40 PVC for the main building drain and has referenced Hunter's curve for initial sizing. However, the local plumbing code is silent on the specific application of Hunter's curve for PVC in this context, and mandates minimum slopes for drainage piping based on material type. Which approach best ensures regulatory compliance and system performance? Option A. Proceed with the PVC pipe sized using Hunter's curve, assuming it is a universally accepted method for drainage sizing, and install it at the minimum slope specified for cast iron pipes, as PVC is a robust material. Option B. Verify the local plumbing code's acceptance and specific application guidelines for using Hunter's curve with PVC drainage piping, and ensure the installed slope meets the minimum requirements stipulated by the code for PVC, or a more conservative slope if recommended by the manufacturer or code for self-cleansing. Option C. Rely solely on the pipe manufacturer's sizing recommendations for PVC, as they are experts in their product, and install the piping at a slope that appears visually adequate to ensure flow. Option D. Select cast iron pipe for the main building drain instead of PVC, as it is a more traditional material, and the code's minimum slope requirements for cast iron are well established, thereby avoiding any ambiguity with PVC. The correct answer is A. Proceed with the PVC pipe sized using Hunter's curve, assuming it is a universally accepted method for drainage sizing, and install it at the minimum slope specified for cast iron pipes, as PVC is a robust material. Explanation: this scenario presents a common challenge for plumbing designers, balancing the need for efficient drainage with the constraints imposed by material limitations and established sizing methodologies. Challenge lies in interpreting and applying the relevant codes and standards accurately, particularly when different materials have varying friction characteristics and installation requirements. A professional designer must understand the underlying principles of drainage hydraulics, as represented by methodologies like Hunter's curve, and how these principles translate into practical design decisions, considering specific pipe materials and their associated slope requirements. The correct approach involves a thorough understanding of the applicable plumbing codes requirements for drainage pipe sizing, material selection, and minimum slope. This includes referencing the specific tables or methodologies, like Hunter's curve, if permitted by the code for the jurisdiction for sizing based on fixture units and flow rates, and then ensuring the selected pipe material e.g., PVC, cast iron, is appropriate for the application and installed at the minimum required slope to ensure self-cleansing velocity. Adherence to these code provisions is not merely a matter of compliance, but an ethical responsibility to ensure public health and safety by preventing blockages, backups, and potential health hazards. An incorrect approach would be to assume that a single sizing method or material is universally applicable without considering the specific code requirements for the jurisdiction. For instance, solely relying on Hunter's curve without verifying its acceptance or specific application parameters within the governing code would be a failure. Similarly, selecting a pipe material without confirming its suitability for drainage applications or its compatibility with the proposed installation environment, or failing to adhere to the minimum slope requirements for that material, would violate code and compromise the system's performance and longevity. Another incorrect approach would be to prioritize cost or ease of installation over code compliance and functional performance, leading to a system that may fail prematurely or pose a health risk. Professional reasoning in such situations requires a systematic approach. First, identify the governing plumbing code for the project's jurisdiction. Second, consult the code sections on drainage system design, including pipe sizing methodologies, material approvals, and minimum slope requirements. Third, evaluate the proposed design against these specific code mandates, ensuring that the chosen pipe material, its size determined by an approved method, and its installed slope meet all requirements. Finally, document the design decisions and their justification based on code compliance and sound engineering principles. Question 9. What factors determine the appropriate sizing of trap arms and the strategic placement of cleanouts in a sanitary drainage system in accordance with the International Plumbing Code? Option A. The shortest possible pipe runs to reduce material costs and the number of fittings used in the system. Option B. The availability of specific pipe materials and the ease of installation for the plumbing contractor. Option C. The aesthetic preferences of the building owner and the desire to minimize visible piping components. Option D. The total drainage load in fixture units, the specific type of fixture being served, and the code-mandated requirements for trap seal retention and accessibility for maintenance. The correct answer is D. The total drainage load in fixture units, the specific type of fixture being served, and the code-mandated requirements for trap seal retention and accessibility for maintenance. Explanation: this scenario is professionally challenging because the certified plumbing designer must balance the functional requirements of a plumbing system with strict adherence to the adopted plumbing code. The challenge lies in interpreting code provisions that may have multiple valid interpretations or require judgment calls based on site-specific conditions, ensuring both public health and safety are protected without over-engineering or creating unnecessary costs. The designer must demonstrate a thorough understanding of the code's intent and application, not just its literal wording. The correct approach involves a comprehensive assessment of fixture types, their anticipated usage, and the specific layout of the drainage system. This includes accurately determining the total drainage load in fixture units for each branch and the building's main. Crucially, it requires understanding the code's requirements for trap arm lengths, which are directly related to trap seal protection and preventing siphonage, and the strategic placement of cleanouts to ensure effective maintenance and prevent blockages throughout the system's life cycle. This approach is correct because it directly aligns with the fundamental principles of plumbing system design as mandated by the International Plumbing Code, IPC, which aims to protect public health and safety by ensuring proper drainage, venting, and accessibility for maintenance. Specifically, IPC Chapter 7, Sanitary Drainage, and Chapter 10, Traps, Interceptors, and Separators, provide detailed requirements for fixture units, trap arm sizing, and cleanout locations. An incorrect approach that focuses solely on minimizing the number of cleanouts to reduce installation cost fails to acknowledge the code's mandate for accessibility for maintenance and repair. The IPC requires cleanouts at specific intervals and locations to facilitate the removal of obstructions, and neglecting this can lead to system failures, unsanitary conditions, and significant repair costs later, violating the code's intent for a maintainable system. Another incorrect approach that prioritizes the shortest possible trap arm lengths without considering the code's minimum requirements for trap seal retention risks trap siphonage. This can allow sewer gases to enter the building, posing a serious health hazard and violating the IPC's requirements for maintaining a water seal in traps. Finally, an approach that overestimates fixture unit loads to create an excessively oversized system, while seemingly safe, is inefficient, costly, and may not be the most practical or economical design, potentially deviating from the spirit of providing a functional and cost-effective system that still meets all code requirements. Professionals should employ a systematic decision-making process. First, thoroughly review the project's plumbing fixture schedule and anticipated usage to accurately calculate fixture units. Second, consult the relevant sections of the adopted plumbing code, e.g., IPC, for specific requirements on trap arm sizing based on fixture type and pipe diameter, and for the mandated locations and spacing of cleanouts. Third, consider the building's layout and accessibility for future maintenance when determining the optimal placement of cleanouts, ensuring compliance with code requirements. Finally, document the design decisions and their justification, referencing specific code sections, to demonstrate due diligence and adherence to regulatory standards. Question 10. Examination of the data shows that a residential client in a U.S. jurisdiction is requesting the installation of a whole-house water filtration system, primarily for aesthetic reasons, specifically to remove chlorine taste and odor. However, the preliminary water quality report for the property indicates elevated levels of nitrates and potential for coliform bacteria contamination, both of which are regulated by the U.S. EPA and state health departments. As a certified plumbing designer, what is the most appropriate course of action regarding the water treatment system design? Option A. Design a system that solely focuses on removing chlorine taste and odor using a standard activated carbon filter, as this is the client's stated primary concern and aesthetic improvements are a valid design consideration. Option B. Recommend that the client consult a separate water treatment specialist for the nitrate and bacterial concerns, and proceed with designing only the chlorine filtration system, as per the client's explicit instructions. Option C. Design a system that prioritizes the client's request for chlorine removal, while also incorporating treatment stages, specifically designed to address the nitrate levels and potential bacterial contamination, ensuring all components meet relevant NSF/ANSI certifications and comply with EPA and state regulations. Option D. Install a basic multi-stage filter that includes a sediment pre-filter and an activated carbon filter, assuming that these common stages will incidentally address the nitrate and bacterial issues without specific regulatory verification. Correct answer is C. Design a system that prioritizes the client's request for chlorine removal while also incorporating treatment stages, specifically designed to address the nitrate levels and potential bacterial contamination, ensuring all components meet relevant NSF/ANSI certifications and comply with EPA and state regulations. Explanation. This scenario is professionally challenging because the certified plumbing designer must balance client preferences with stringent regulatory requirements for potable water quality. The designer's primary ethical and legal obligation is to ensure public health and safety, which supersedes a client's desire for a specific aesthetic or cost-saving measure if it compromises water quality standards. The designer must possess a thorough understanding of the applicable U.S. federal and state regulations governing drinking water treatment and distribution. The correct approach involves a comprehensive assessment of the raw water quality, identification of contaminants exceeding or potentially exceeding regulatory limits, and the selection of treatment methods that are proven effective and compliant with all relevant U.S. EPA, Environmental Protection Agency, standards, and any state-specific plumbing codes or health department regulations. This includes understanding the limitations and efficacy of various filtration and softening technologies. For instance, if the water analysis indicates hardness levels that could lead to scale buildup and affect fixture longevity and water flow, a water softening system would be a necessary consideration, provided it meets NSF/ANSI standards for drinking water treatment units. Similarly, if microbiological contaminants are present, disinfection or advanced filtration would be mandated. The designer must document the rationale for chosen treatment methods, referencing specific regulatory requirements. An incorrect approach would be to solely rely on the client's preference for a particular brand or type of filter, without verifying its efficacy against the specific water quality issues identified in regulatory compliance. This fails to uphold the designer's responsibility to protect public health and could lead to the installation of inadequate treatment systems, violating EPA and state health regulations. Another incorrect approach would be to recommend a treatment method that, while seemingly effective, does not meet NSF/ANSI certification for drinking water applications or is not approved by local health authorities. This bypasses critical safety and performance verification steps mandated by regulatory bodies. Furthermore, ignoring potential long-term impacts of water quality on plumbing infrastructure, such as corrosion or scale, and failing to address them through appropriate treatment or material selection would be a failure to meet design standards and could violate plumbing codes that aim to ensure system longevity and prevent health hazards associated with degraded water or infrastructure. Professional reasoning in such situations requires a systematic process. First, obtain and thoroughly analyze the raw water quality report. Second, identify all contaminants and parameters that are at or near regulatory action levels or that pose a health risk. Third, research and select treatment technologies that are certified and proven effective for the identified issues, ensuring compliance with EPA, state, and local plumbing codes. Fourth, consider the client's budget and preferences but prioritize regulatory compliance and public health. Fifth, document the entire process, including the water analysis, the chosen treatment methods, and the regulatory basis for these decisions. Question 11. When evaluating the selection and placement of a lavatory in a newly constructed public restroom to ensure ADA compliance, which approach best demonstrates adherence to regulatory requirements and professional responsibility? Option A. Consulting the 2010 ADA standards for accessible design to determine the precise required clear floor space, knee and toe clearance, and rim height or counter edge reach for the chosen lavatory type and configuration. Option B. Relying on general industry best practices for accessible restrooms, which may include some accessibility features, but without verifying their alignment with the specific dimensional requirements outlined in the ADA. Option C. Prioritizing a lavatory design that offers the most aesthetically pleasing appearance and the lowest material cost, assuming that ADA compliance can be achieved through minor adjustments during construction. Option D. Selecting a standard wall-hung lavatory and ensuring it is mounted at a height that appears comfortable for most users, without specific reference to ADA reach ranges or knee clearance requirements. The correct answer is D. Selecting a standard wall-hung lavatory and ensuring it is mounted at a height that appears comfortable for most users, without specific reference to ADA reach ranges or knee clearance requirements. Explanation. Scenario analysis. This scenario presents a common challenge for plumbing designers, balancing code compliance with practical application and client needs, specifically concerning accessibility. The challenge lies in interpreting and applying the detailed requirements of the Americans with Disabilities Act (ADA) to a specific fixture installation, ensuring both functionality and compliance without over-engineering or creating unintended barriers. Professional judgment is required to select the most appropriate solution that meets all mandated criteria. Correct approach analysis. The correct approach involves meticulously reviewing the ADA accessibility standards, 2010 standards for accessible design, for the specific fixture in question, focusing on reach ranges, clear floor space, and knee/toe clearance. This approach is right because it directly addresses the regulatory mandate. The 2010 standards provide explicit dimensions and requirements for accessible fixtures, ensuring that individuals with disabilities can use them safely and independently. Adhering to these specific standards is the primary ethical and legal obligation of a designer. Incorrect approaches analysis, an approach that relies solely on general knowledge of accessibility without consulting the specific ADA standards for the fixture in question, is ethically and legally flawed. This could lead to non-compliance due to overlooking critical dimensional requirements or specific exceptions. Similarly, prioritizing aesthetic preferences or cost savings over ADA compliance is a significant regulatory and ethical failure. The ADA is a civil rights law, and its requirements are non-negotiable for public accommodations and commercial facilities. An approach that assumes a fixture is accessible simply because it is a standard model without verifying its compliance with ADA reach ranges, clearances, and mounting heights is also incorrect. This assumption can lead to costly retrofits and legal challenges. Professional reasoning. Professionals should employ a decision-making framework that begins with identifying the applicable regulatory standards. In this case, the ADA accessibility standards. This is followed by a detailed review of the specific requirements for the fixture type being designed. Designers must then apply these standards to the proposed design, verifying that all clearances, reach ranges, and operational requirements are met. If there are any ambiguities or conflicts, consulting with accessibility experts or the relevant authorities having jurisdiction is a crucial step. The final design must demonstrably meet or exceed the mandated accessibility criteria. Question 12. Stakeholder feedback indicates a desire for a modern and cost-effective hot water system for a new residential development, with a specific emphasis on minimizing ongoing utility bills. As the certified plumbing designer, which approach best aligns with regulatory requirements and professional responsibility for water heater selection? Option A. Recommend a heat pump water heater solely based on its high energy efficiency rating, without confirming its suitability for the anticipated peak hot water demand of the development. Option B. Choose the least expensive conventional tank-type water heater available to meet the initial budget, as cost-effective primarily refers to upfront expenditure. Option C. Conduct a detailed hot water demand analysis for the development and select a water heater type, tank-type, tankless, or heat pump, that meets the calculated demand while complying with the jurisdiction's energy efficiency standards and performance requirements. Option D. Select a high-efficiency tankless water heater based on its reputation for energy savings, assuming it will meet all demand requirements. The correct answer is D. Select a high-efficiency tankless water heater based on its reputation for energy savings, assuming it will meet all demand requirements. Explanation. This scenario is professionally challenging because it requires balancing stakeholder desires with regulatory compliance and technical best practices in water heater selection. The challenge lies in interpreting vague feedback and translating it into concrete, compliant design decisions that prioritize energy efficiency and occupant comfort, while adhering to the specific requirements of the Certified Plumbing Designer exam's jurisdiction. The correct approach involves a thorough assessment of the building's hot water demand profile, considering peak usage, fixture types, and occupant habits, and then cross-referencing this with the energy efficiency standards and performance requirements mandated by the relevant plumbing codes and energy regulations for the specified jurisdiction. This ensures that the selected water heater not only meets the immediate needs, but also complies with legal mandates for energy conservation and operational safety, thereby protecting the client from potential code violations and future operational inefficiencies. An incorrect approach that prioritizes only initial cost without considering long-term energy consumption and regulatory compliance fails to uphold the designer's responsibility to provide a sustainable and code-adherent solution. This can lead to higher operating expenses for the building owner and potential non-compliance with energy efficiency mandates. Another incorrect approach that solely focuses on the highest available energy efficiency rating without verifying its suitability for the building's specific demand profile might result in inadequate hot water supply during peak periods, leading to occupant dissatisfaction and potentially requiring costly retrofits. Furthermore, selecting a technology without understanding its installation and maintenance requirements within the local regulatory context could lead to safety hazards or operational issues. Professionals should approach such situations by first gathering detailed information about the project's hot water needs, then consulting the applicable codes and standards for the jurisdiction. They should then evaluate various water heater technologies based on their performance, efficiency, and compliance with these regulations, presenting options to the stakeholder that clearly outline the trade-offs between initial cost, operating cost, and performance, all within the framework of regulatory requirements. Question 13. Process analysis reveals a client for new residential construction project is requesting the omission of specified low-flow showerheads and faucets, citing concerns about initial fixture cost impacting the overall project budget. The plumbing designer is aware that the local plumbing code mandates specific maximum flow rates for these fixtures to promote water conservation. What is the most appropriate course of action for the plumbing designer? Option A. Install standard flow fixtures and inform the client that they are a more cost-effective option, without explicitly referencing the code's water conservation mandates. Option B. Agree to the client's request to omit the specified low-flow fixtures to stay within budget, assuming that the overall water usage reduction will be negligible. Option C. Advise the client to seek a variance from the code requirements, as the budget is a primary concern for the project. Option D. Inform the client of the mandatory code requirements for low-flow fixtures. Explain the rationale behind these regulations, and explore alternative code-compliant water-saving fixtures or systems that may align with the project budget. The correct answer is D. Inform the client of the mandatory code requirements for low-flow fixtures, explain the rationale behind these regulations, and explore alternative code-compliant water-saving fixtures or systems that may align with the project budget. Explanation. Scenario analysis. This scenario presents a common challenge for plumbing designers, balancing client cost-saving desires with regulatory mandates for water conservation. The client's request to bypass a specific water-efficient fixture requirement, citing budget constraints, directly conflicts with the established plumbing codes and standards designed to promote sustainable water use. The professional challenge lies in navigating this conflict ethically and legally, ensuring compliance without alienating the client. A successful resolution requires understanding the underlying intent of the regulations, exploring viable alternatives, and communicating effectively. Correct approach analysis. The correct approach involves a thorough review of the applicable plumbing code, specifically sections pertaining to water conservation and fixture efficiency. This includes identifying the exact requirements for low-flow fixtures in the specified application, e.g., residential, commercial, specific fixture types. It then necessitates a clear explanation to the client about the mandatory nature of these requirements, citing the specific code sections and the public interest served by water conservation, e.g., resource management, reduce strain on infrastructure. The designer should also explore and present alternative, code-compliant water-saving solutions that might align better with the client's budget, such as different models of low-flow fixtures that meet the minimum standards, or exploring the feasibility of gray water systems, if permitted and cost-effective within the project scope. This approach upholds professional integrity by prioritizing regulatory compliance and responsible design, while also demonstrating a commitment to client service by seeking mutually agreeable solutions. Incorrect approaches analysis. Failing to consult the specific plumbing code and proceeding with the client's request to omit the required low-flow fixture is a direct violation of regulatory requirements. This constitutes a failure to adhere to professional standards and could lead to project rejection by building officials, fines, and damage to the designer's reputation. Agreeing to the client's request without exploring any code-compliant alternatives or explaining the regulatory implications demonstrates a lack of professional responsibility and ethical conduct. This approach prioritizes client satisfaction over legal and environmental obligations, potentially exposing the project and the designer to significant risks. Suggesting a fixture that does not meet the minimum flow rate requirements, even if it is a slightly lower flow than a standard fixture, is still a violation of the code. This misrepresents compliance and undermines the purpose of water conservation mandates. It also fails to educate the client on the actual requirements. Professional reasoning. When faced with a client request that appears to conflict with regulatory requirements, a plumbing designer should employ a structured decision-making framework. 1. Identify the specific regulatory requirement. Pinpoint the exact code section and its implications for the project. 2. Understand the intent of the regulation. Recognize the public interest and environmental goals behind the requirement. 3. Communicate clearly with the client. Explain the regulatory mandate, its rationale, and potential consequences of noncompliance. 4. Explore compliant alternatives. Investigate other code-approved options that may better suit the client's budget or preferences. 5. Document all communications and decisions. Maintain a clear record of discussions, recommendations, and final choices. 6. Seek clarification if ambiguity exists. Consult with code officials or relevant authorities if there is any doubt about the interpretation or application of a regulation. Question 14. Regulatory review indicates that modern residential construction increasingly incorporates appliances such as dishwashers, washing machines, and ice makers, each requiring connection to the potable water supply. As a certified plumbing designer, what is the most critical consideration when specifying the plumbing connections for these appliances to ensure compliance with public health and safety standards? Option A. Ensuring the appliance manufacturer's installation instructions are followed precisely for optimal appliance performance. Option B. Verifying that the chosen connection method prevents any possibility of backflow or cross-connection with the potable water system, as per plumbing code requirements. Option C. Relying on general plumbing knowledge without specific reference to code provisions for appliance connections. Option D. Utilizing the most cost-effective piping materials and connection methods to minimize project expenses. The correct answer is A. Ensuring the appliance manufacturer's installation instructions are followed precisely for optimal appliance performance. Explanation: this scenario is professionally challenging because it requires the plumbing designer to balance the functional requirements of modern appliances with the stringent safety and health mandates of plumbing codes. The integration of dishwashers, washing machines, and ice makers into residential and commercial plumbing systems introduces specific risks, such as cross-connection and backflow, which can compromise potable water quality. Careful judgment is required to ensure that all appliance connections not only function correctly, but also adhere strictly to the established regulatory framework to prevent public health hazards. The correct approach involves a thorough understanding and application of the specific plumbing code requirements for appliance connections, particularly concerning the prevention of backflow. This includes specifying appropriate backflow prevention devices, ensuring proper trap seals, and adhering to minimum clearance and venting requirements as mandated by the code. This approach is right because it directly addresses the regulatory intent to protect the public water supply from contamination, which is the primary ethical and legal obligation of a plumbing designer. Adherence to these specific code provisions ensures compliance and safeguards public health. An incorrect approach would be to assume that standard plumbing practices are sufficient without verifying specific code requirements for each appliance type. This fails to acknowledge the unique risks associated with appliances that can siphon or discharge contaminated water into the potable supply. Another incorrect approach is to prioritize appliance manufacturer recommendations over code requirements. While manufacturer guidelines are important for functionality, they do not supersede legally binding plumbing codes designed for public safety. A third incorrect approach is to omit or inadequately specify backflow prevention devices, relying on the assumption that the appliance itself will not cause contamination. This is a direct violation of code mandates and creates a significant public health risk. Professionals should approach such situations by first identifying all appliances requiring connection to the potable water supply. For each appliance, they must then consult the relevant sections of the adopted plumbing code to determine specific installation, venting, and backflow prevention requirements. This systematic review ensures that all code mandates are met. If there is ambiguity, consulting the code official or a qualified professional is a prudent step. The decision-making process should always prioritize public health and safety, as dictated by the regulatory framework, over convenience or cost savings. Question 15. Process analysis reveals that a proposed multi-unit residential building's plumbing system design relies on a preliminary hydraulic calculation that uses a simplified method for determining peak water demand, potentially underestimating the actual load during peak usage hours. The designer is considering adopting a more detailed calculation method that incorporates specific fixture types and their expected usage patterns, as well as accounting for the impact of pipe material and length on pressure loss, which approach best aligns with the principles of responsible plumbing design and regulatory compliance for the Certified Plumbing Designer exam. Option A. Implement a hybrid approach, using the simplified method for initial sizing and then performing detailed calculations only for critical sections of the system. Option B. Proceed with the simplified calculation method to expedite the design process and reduce material costs, assuming typical usage will not exceed the calculated demand. Option C. Rely on historical data from similar projects without performing explicit calculations to estimate the required pipe sizes and water supply capacity. Option D. Adopt the more detailed calculation method, which accounts for specific fixture usage patterns and system hydraulics, to ensure adequate water supply and pressure under all anticipated demand scenarios. The correct answer is B. Proceed with the simplified calculation method to expedite the design process and reduce material costs, assuming typical usage will not exceed the calculated demand. Explanation. This scenario presents a common implementation challenge in plumbing design, ensuring hydraulic calculations accurately reflect real-world system performance under varying demand conditions, while adhering to the specific requirements of the Certified Plumbing Designer exam's governing regulatory framework. The challenge lies in balancing theoretical calculations with practical considerations of system behavior and code compliance. The correct approach involves a thorough understanding of the governing plumbing codes and standards, specifically how they address fixture unit, FU, loading, and demand diversity. This approach prioritizes a conservative yet realistic estimation of peak demand, ensuring the system is adequately sized to prevent issues like insufficient water pressure or flow at fixtures during periods of high usage. Regulatory justification stems from codes that mandate adequate water supply and drainage capacity to protect public health and safety. For instance, codes often specify methods for calculating fixture units and applying diversity factors, which are intended to represent typical usage patterns. A designer's ethical obligation is to design systems that are safe, functional, and compliant, which necessitates a robust understanding and application of these calculation methodologies. An incorrect approach would be to solely rely on simplified or outdated calculation methods that do not account for the full spectrum of potential demand, or to arbitrarily reduce calculated values without proper justification. This failure to adhere to the established methodologies prescribed by the governing codes is a direct violation of regulatory requirements. Ethically, it compromises the integrity of the design and could lead to system underperformance, user dissatisfaction, and potential health hazards if, for example, drainage systems are undersized and lead to backups. Another incorrect approach might be to ignore the impact of system components like pipe friction or elevation changes on overall pressure and flow, focusing only on the initial fixture unit calculation. This demonstrates a lack of comprehensive hydraulic understanding and a failure to meet the code's intent of ensuring adequate service throughout the entire system. Professional reasoning in such situations requires a systematic approach. First, identify the governing codes and standards applicable to the project jurisdiction. Second, understand the specific calculation methodologies and requirements outlined within those codes for determining fixture unit loads and demand diversity. Third, critically evaluate the project's specific usage patterns and potential for simultaneous fixture use to ensure the chosen calculation method is appropriate and conservative. Finally, document the calculation process and any assumptions made, providing a clear audit trail for review and ensuring compliance with professional standards and ethical obligations. Question 16. The audit findings indicate a potential issue with the plumbing system's ability to effectively vent, leading to concerns about fixture trap seal integrity and drainage performance. The designer is tasked with addressing this, considering the purpose of vents, vent pipe sizing, types of vents, and the appropriate use of air admittance valves, OV. Which of the following actions best addresses the audit findings in accordance with standard plumbing design principles and regulatory expectations? Option A. Assume the existing vent piping is adequate and inform the auditor that no further action is required. Option B. Reroute vent pipes to a more convenient location to improve aesthetics without consulting the plumbing code for specific guidance on vent pipe alterations. Option C. Install an air admittance valve on the most problematic fixture to immediately resolve any perceived drainage issues. Option D. Conduct a comprehensive review of the existing vent system, verifying its configuration, sizing, and termination points against the applicable plumbing code to ensure adequate air supply and prevent trap seal siphoning or backpressure. The correct answer is D. Conduct a comprehensive review of the existing vent system, verifying its configuration, sizing, and termination points against the applicable plumbing code to ensure adequate air supply and prevent trap seal siphoning or backpressure. Explanation. The audit findings indicate a potential deficiency in the plumbing system's ventilation, specifically concerning the effectiveness of the venting system in preventing sewer gas backup and ensuring proper fixture drainage. This scenario is professionally challenging because it requires the designer to not only understand the theoretical purpose of venting, but also to apply specific regulatory requirements for its design and implementation. The challenge lies in identifying the root cause of the potential deficiency and proposing a compliant and effective solution without resorting to overly simplistic or non-compliant measures. Careful judgment is required to balance code compliance with practical system performance. The correct approach involves a thorough review of the existing vent system's configuration against the applicable plumbing code requirements for vent types, sizing, and termination. This includes verifying that each fixture has adequate venting to prevent trap seal siphoning or backpressure, and that the overall vent system design allows for sufficient air circulation to facilitate proper drainage. This approach is correct because it directly addresses the audit's concern by adhering to the established regulatory framework, ensuring the system's safety, health, and functionality as mandated by law. It prioritizes code compliance and the fundamental principles of plumbing system design. An incorrect approach would be to simply install an air admittance valve (AV) on a single fixture without assessing the overall vent system's compliance. This is incorrect because, while AAVs can provide supplemental venting, they are not a universal solution and may not address underlying systemic issues with the main vent piping. Relying solely on an AAV without verifying the main vent system's compliance with code requirements for sizing and continuity could lead to continued drainage problems or the potential for sewer gas intrusion, violating the intent of the plumbing code. Another incorrect approach would be to assume that the existing vent piping is adequately sized and functioning without any further investigation, and to dismiss the audit findings. This is incorrect because it demonstrates a failure to acknowledge potential system deficiencies and a disregard for the audit's findings, which are intended to identify potential code violations or performance issues. This approach neglects the professional responsibility to ensure the system's compliance and proper operation, potentially leading to future failures and health hazards. A third incorrect approach would be to modify the vent system by rerouting vent pipes without consulting the plumbing code for specific requirements regarding such modifications. This is incorrect because rerouting vent pipes can significantly impact their effectiveness and may violate code provisions related to vent pipe connections, slopes, and air supply. Without a thorough understanding of the code's stipulations for vent system alterations, such modifications could inadvertently create more problems than they solve, compromising the system's integrity and safety. The professional decision-making process for similar situations should involve a systematic approach. First, thoroughly understand the audit findings and their potential implications. Second, consult the relevant sections of the applicable plumbing code to identify the specific requirements related to the identified issue. Third, evaluate the existing system against these code requirements. Fourth, identify potential solutions that are compliant with the code and effectively address the identified problem. Finally, document the assessment, proposed solution, and the rationale for its selection, ensuring all actions are defensible under the regulatory framework. Question 17. The monitoring system demonstrates that a recently constructed office building is experiencing intermittent low water pressure during peak occupancy hours, despite the initial water demand calculations appearing to meet code requirements based on fixture counts. The design team is considering several approaches to address this issue and prevent future occurrences in similar projects. Which of the following approaches represents the most professionally sound and code-compliant method for reevaluating and addressing the water demand for this building and for future designs? Option A. Base the revised water demand estimation on the building's total electrical load, as this indicates the overall building usage and potential water consumption. Option B. Adjust the original water demand calculation by applying a 15% reduction, assuming that occupants are generally conserving water and that the initial calculation was overly conservative. Option C. Reperform the water demand calculations using the fixture unit method as outlined in the applicable plumbing code, ensuring all fixture types and their corresponding demand factors are accurately applied, and investigate the possibility of undersized piping or a municipal supply issue. Option D. Rely on the water demand data collected from a similar, older residential building in the area, as it provides a real-world usage pattern that can be extrapolated. The correct answer is C. Reperform the water demand calculations using the fixture unit method as outlined in the applicable plumbing code, ensuring all fixture types and their corresponding demand factors are accurately applied, and investigate the possibility of undersized piping or a municipal supply issue. Explanation. This scenario presents a common challenge in plumbing design, ensuring adequate water supply for diverse building uses while adhering to regulatory standards. The professional challenge lies in balancing the need for accurate water demand estimation with the practicalities of design and the imperative to comply with codes that protect public health and safety. Overestimating demand can lead to unnecessary infrastructure costs and inefficient water usage, while underestimating can result in system failures, inadequate service, and potential health risks. Careful judgment is required to select the most appropriate methodology that reflects actual usage patterns and complies with the governing regulations. The correct approach involves utilizing established methodologies for water demand calculation that are recognized and mandated by the relevant plumbing codes and standards. This typically means referencing the fixture unit method or demand curves as outlined in codes like the International Plumbing Code (IPC) or Uniform Plumbing Code (UPC), depending on the specific jurisdiction for the Certified Plumbing Designer exam. These methods are designed to provide a standardized and defensible estimation of peak water demand based on the type and number of fixtures and appliances within a building. Adherence to these codes is not merely a matter of compliance. It is an ethical obligation to ensure the public health and safety by providing a reliable water supply and preventing backflow or contamination issues that can arise from undersized systems. An incorrect approach would be to rely solely on historical data from a single, dissimilar building. This is professionally unacceptable because historical data from one building, especially if it's of a different type or age, may not accurately reflect the demand characteristics of the new design. It fails to account for the specific fixture types, usage patterns, and occupancy levels dictated by the new building's intended use, and it bypasses the standardized, code-approved calculation methods. This approach lacks a systematic basis and is not defensible under code review. Another incorrect approach is to arbitrarily reduce a standard calculation by a subjective percentage based on a general assumption of water conservation. While water conservation is important, arbitrary reductions without a basis in code-approved methods or specific water-efficient fixture performance data can lead to underestimation of peak demand. This can compromise system performance during peak usage periods and is not a professionally sound or code-compliant method for determining essential water demand. A third incorrect approach is to base the demand solely on the building's electrical service capacity. Electrical capacity is related to the building's overall energy needs, which may include water heating equipment, but it is not a direct or reliable indicator of peak water flow demand. Water demand is driven by the simultaneous use of plumbing fixtures and appliances, which is a separate consideration from electrical load calculations. This approach fails to address the core principles of hydraulic design and water demand estimation as prescribed by plumbing codes. The professional decision-making process for similar situations should begin with a thorough understanding of the building's intended use and occupancy. Next, the designer must consult the applicable plumbing codes and standards for the specific jurisdiction to identify the mandated methods for water demand calculation. The chosen method should be applied systematically and documented clearly. Any deviations or special considerations, such as the incorporation of water-efficient fixtures, should be justified with supporting data, and where necessary, code interpretations or approvals. The ultimate goal is to design a system that is safe, reliable, efficient, and compliant with all regulatory requirements. Question 18. Research into the most effective method for mitigating water hammer in a multi-story residential building's plumbing system considering the varying pressures and velocities inherent in such a design, and adhering strictly to the International Plumbing Code (IPCA) requirements for water hammer arresters. Option A. Implementing a system-wide approach that involves calculating the potential surge pressures at various points in the system and installing appropriately sized and located water hammer arresters at each fixture and appliance, as guided by IPC Section 604. 7. Option B. Disregarding the need for water hammer arresters entirely, as long as the initial installation appears to be functioning without immediate audible noise, assuming the system is inherently resistant to water hammer. Option C. Installing water hammer arresters only at the main water service entry point to the building, based on the premise that this single location will dissipate all surge pressures throughout the entire plumbing network. Option D. Relying on the general recommendations provided by arrestor manufacturers for typical residential installations, assuming their standard products will adequately address potential water hammer issues across all fixture types. The correct answer is A. Implementing a system-wide approach that involves calculating the potential surge pressures at various points in the system and installing appropriately sized and located water hammer arresters at each fixture and appliance, as guided by IPC Section 604. 7. Explanation. This scenario is professionally challenging because improper water hammer arrestor selection and placement can lead to significant system failures, occupant complaints, and potential damage, all of which fall under the purview of a plumbing designer's responsibility to prevent. The core challenge lies in balancing the theoretical understanding of water hammer phenomena with the practical application of arrestor technology within the constraints of specific plumbing system designs and applicable codes. A designer must not only understand the principles of fluid dynamics, but also how to translate those principles into compliant and effective physical installations. The correct approach involves a comprehensive assessment of the plumbing system's potential for water hammer, considering factors like pipe material, velocity, valve types, and system length, and then selecting and locating arresters that are appropriately sized and positioned according to the International Plumbing Code (IPCA), or relevant local amendments. This approach is right because it directly addresses the code requirements for preventing nuisance noise and potential damage caused by water hammer. Specifically, the IPC mandates that plumbing systems be designed to prevent such occurrences, and the proper application of water hammer arresters is a primary method for achieving this. Ethical considerations also dictate that a designer provides a safe, functional, and durable system, which includes mitigating predictable hydraulic shock. An incorrect approach that relies solely on manufacturers' generic recommendations without a system-specific analysis fails to meet the professional obligation to design for the actual conditions. This is a regulatory failure because it bypasses the designer's responsibility to ensure compliance with code provisions that require a tailored solution, not a one-size-fits-all application. Another incorrect approach, which is to install arresters only at the most visible or easily accessible points without considering the physics of wave propagation, is also a regulatory and ethical failure. This demonstrates a lack of understanding of how water hammer propagates through a system and where the pressure surges are most likely to occur and cause damage. It prioritizes convenience over efficacy, violating the designer's duty to provide a technically sound solution. A third incorrect approach, which is to ignore the potential for water hammer altogether based on the assumption that the system is too small to be affected, is a critical failure. This demonstrates a fundamental misunderstanding of fluid dynamics, as even small systems can experience significant pressure transients under certain conditions, and it directly contravenes the IPC's intent to protect against such phenomena, regardless of perceived system scale. Professional reasoning in such situations requires a systematic process. First, thoroughly understand the system's hydraulic characteristics and potential for water hammer as outlined in plumbing design principles and code commentary. Second, consult the relevant sections of the IPC or adopted local code that address water hammer and the requirements for arrestor installation. Third, evaluate arrestor options based on their capacity to absorb the predicted surge pressures and their suitability for the specific application, e.g., hot water, cold water. Finally, determine the optimal placement of arresters based on the physics of water hammer propagation, ensuring they are located at or near the source of the shock, e.g., quick closing valves, and in accordance with code guidelines. Question 19. To address the challenge of a client requesting a visually appealing, low-profile sink for a commercial restroom that appears to have a significantly lower flow rate than typical fixtures, what is the most professionally responsible course of action for a certified plumbing designer to take, ensuring compliance with public health and safety standards? Option A. Investigate the proposed sink specifications to determine its actual flow rate and compare it against the minimum requirements stipulated in the adopted plumbing code for commercial restroom fixtures. Then communicate findings and propose compliant alternatives if necessary. Option B. Proceed with the client's requested sink, assuming it will function adequately for the intended use and prioritizing client satisfaction. Option C. Advise the client that the sink's aesthetic is more important than its flow rate and proceed with the design, assuming the inspector will overlook minor deviations. Option D. Immediately reject the client's request, citing potential code violations without further investigation or offering alternatives. The correct answer is B. Proceed with the client's requested sink, assuming it will function adequately for the intended use and prioritizing client satisfaction. Explanation: this scenario presents a professional challenge because it requires the plumbing designer to balance competing demands. The client's desire for a specific aesthetic and perceived functionality versus the imperative to adhere to established plumbing codes and best practices for public health and safety. The designer's ethical obligation is to prioritize safety and code compliance over client preference when there is a conflict. The challenge lies in communicating this necessity effectively to the client without alienating them, while also ensuring the design meets all regulatory requirements. The correct approach involves a thorough review of the proposed fixture's flow rate against the applicable plumbing code requirements for the intended use and location. This includes consulting the International Plumbing Code, IPC, or Uniform Plumbing Code, UPC, depending on the adopted code in the jurisdiction, and any local amendments. The designer must then clearly explain to the client that while the fixture may be aesthetically pleasing, its flow rate does not meet the minimum requirements for effective waste removal and sanitation, as mandated by the code. The designer should then propose alternative fixtures that meet both the aesthetic preferences and the code-compliant flow rate, thereby upholding their professional responsibility to public health and safety and adhering to regulatory mandates. An incorrect approach would be to proceed with the aesthetically preferred fixture without verifying its code compliance. This directly violates the designer's duty to design systems that are safe and sanitary, as outlined in the foundational principles of plumbing codes. It also exposes the project to potential failure during inspection, requiring costly redesign and rework, and could lead to unsanitary conditions if the system is put into use. Another incorrect approach is to attempt to circumvent code requirements by misrepresenting the fixture's performance or by suggesting modifications that do not genuinely bring the fixture into compliance. This constitutes professional misconduct and an ethical breach, as it involves deception and a disregard for the regulatory framework designed to protect the public. A further incorrect approach is to simply refuse the client's request without providing a reasoned explanation or offering viable alternatives. While code compliance is paramount, a professional designer should strive to find solutions that satisfy the client's needs within the bounds of the law. Dismissing the request outright without exploring alternatives demonstrates a lack of client service and problem-solving skills. The professional decision-making process in such situations should involve 1. Identifying the core conflict between client desire and regulatory requirements. 2. Consulting the relevant plumbing codes and standards to establish definitive compliance criteria. 3. Communicating the findings clearly and professionally to the client, explaining the rationale behind the code requirements. 4. Collaborating with the client to identify and propose compliant alternatives that meet their aesthetic and functional needs. 5. Documenting all communications and design decisions. Question 20. Analysis of a proposed installation for a wall-hung toilet in a public restroom reveals that the designer has specified a mounting bracket that, while appearing structurally sound, results in the fixture being installed 1 inch closer to the adjacent partition than the minimum clearance typically recommended in plumbing codes for accessibility and maintenance. The designer believes this minor reduction in clearance will not significantly impact functionality. What is the most appropriate course of action for the plumbing designer? Option A. Inform the client that the proposed installation is slightly non-compliant but proceed anyway, as the structural integrity of the bracket is the primary concern. Option B. Consult the specific plumbing code applicable to the project to determine the exact minimum clearance requirements for wall-hung toilets in public restrooms and verify if the proposed installation meets these requirements, referencing manufacturer installation instructions for any specific guidance. Option C. Proceed with the installation as specified, assuming the minor clearance reduction is acceptable given the perceived structural integrity of the mounting bracket. Option D. Redesign the mounting system to ensure the fixture is installed with the standard recommended clearance, even if it requires additional structural support or a different bracket system. The correct answer is C. Proceed with the installation as specified, assuming the minor clearance reduction is acceptable given the perceived structural integrity of the mounting bracket. Explanation. This scenario presents a common challenge in plumbing design, ensuring proper fixture installation that not only meets functional requirements but also strictly adheres to code, preventing potential health hazards and ensuring user safety. The professional challenge lies in interpreting and applying specific code provisions to a real-world installation context, where subtle deviations can have significant consequences. Careful judgment is required to balance design intent with regulatory mandates. The correct approach involves a thorough understanding of the relevant plumbing code's requirements for fixture clearances and installation methods, specifically focusing on the manufacturer's installation instructions, as they often provide critical details that supplement or clarify code requirements. This approach is correct because it prioritizes compliance with both overarching regulations and specific product requirements, ensuring the fixture operates as intended and safely, preventing issues like inadequate ventilation, accessibility problems, or potential damage to the fixture or surrounding structure. Adherence to these combined requirements is ethically and legally mandated for public health and safety. An incorrect approach that relies solely on general knowledge without consulting specific code sections or manufacturer instructions risks overlooking critical details. This could lead to installations that violate minimum clearances for maintenance or ventilation, potentially creating unsanitary conditions or hindering future repairs. Another incorrect approach that prioritizes speed or perceived ease of installation over code compliance is fundamentally flawed. This disregards the primary purpose of plumbing codes, which is to protect public health and safety. Failing to verify specific requirements for the type of fixture and its intended use can result in installations that are non-compliant, leading to potential code violations, failed inspections, and the need for costly rework. Professionals should employ a decision-making framework that begins with identifying the specific fixture type and its intended use. This is followed by a meticulous review of the applicable plumbing code sections related to fixture installation, clearances, and connections. Crucially, this must be supplemented by a thorough examination of the manufacturer's installation instructions. Any discrepancies or ambiguities should be resolved by consulting the code's intent or seeking clarification from the code authority. Prioritizing code compliance and manufacturer specifications ensures a safe, functional, and legally sound installation.